干嘛？
Hey guys. So, we meet again. Let's see. We started talking about priority queues last time because we're gonna meet some algorithms later, maybe in this lecture, maybe tomorrow, where we're gonna need this data structure, where it basically supports the operation of performs these operations of inserting an element into the data set and finding the minimum, with the element with the minimum key value or the maximum key value, very efficiently. Plus some other operations that we talked about, the delete operation, decrease key operation, and extract max or extract min, depending on if it's a max heap or a min heap. So we talked about all those operations with respect to the implementation of priority queue as a binary heap. And we talked about the complexity of those operations. So you remember find min was or find max. That was only a constant time operation. The insert operation cost us log n. The delete cost us log n. Decrease key was log n. Pretty much everything else was log n. The only other operation I want to talk about with respect to binary heap before we close that chapter is the actual construction of the binary heap. So how long do you think it takes us to construct the binary heap of, let's say, n elements? All right, so a lot of you guys are saying that the construction is going to take O of n log n. So yes, that, can be done in O of n log n very easily, basically using n insert operations, right? So each insert takes log n time, and the whole thing is going to take n log n time. But can we do better? You'll see me asking this question over and over again. Can we do better? And it is actually possible to do better with the construction of the binary heap. And the trick to do this is to not use the insert operation to get a better performance, but to actually, somebody commented that O of n log n, it's a loose bound. Yes. That's right. So it can be done in O of n log n, but if you actually perform n insert operations, O of n log n is actually a tight bound. But if you do it with a different approach, you could actually bring the complexity down a bit. So the trick to do it, to bring the complexity down, is not to use the insert operation and to build the priority queue, or basically the binary heap, to build it bottom up instead of top down. So the way to do this, I would give you an example where we have a full binary tree, because it's easier to see it that way, but it applies to special cases where you have complete binary trees as well. All right, so the way to do this is to construct the heap bottom up. Okay, so you remember this whole construction is happening inside an array, right? So the whole binary tree, the binary heap, it just consists of a binary tree which is held within an array. right? So we have, let's say, n elements, right? And they basically form a full binary tree, right? So the bottom portion of this array can be thought of as a set of heaps of size 1. So you could imagine that you already have heaps of size 1 at the end of this array. Okay. So then these heaps, I mean, since there's only one level involved in them, they have the heap property satisfied. So you can just say there are heaps of size 1 sitting at the bottom of the array. Now you're going to construct heaps of size 3, right? So you're going to take into consideration the parent, because we know how to compute the position of the parent of this node in a full binary heap. So you could basically say, okay, who the parent is, and then you could make sure that these heaps of size 3 satisfy the heap property, right? And so over here, we basically had to do 0 operations to create these heaps of size 1, right? At this level, we only have to perform how many operations to make sure that that these heaps satisfy the heap property, to make sure that the key value here is greater than the key value, for example, of these two children. How many swaps do you have to do at most? So how many swaps, like how many levels do you have to go down to perform a swap to make sure that this is a 1, right? So you only need 1 swap. So let's change this in terms of instead of operations. So at this level, you can only do 1 swap and guarantee that that these heaps of size 3 satisfy the heap property. Now let's go 1 level above that. At this level, how many swaps do you have to do to make sure that this is, that's right, 2 swaps. The only level, so you could basically keep going up, the only level at which you have to do log n swaps at most, that is there's only one element for which you have to do that, right? And that's the element at the very top of the heap, right? So at the very bottom, if there are n elements in this full binary tree, then how many elements do you have at the very bottom? Basically have n over 2 of them at the very bottom, right? At this level above it, you have n over 4. This level above that, n over 8, and all the way up to 1. Okay? So you see that for the majority of the elements, you're performing really no operations, 0 swaps to put them into the heap. For n over 4 of them, you're doing 1 swap. For n over 8 of them, you're doing 2 swaps. So if you add all of this up, it doesn't go beyond linear time, right? So you're only doing one element that has to have at most log n swaps associated with it. Okay, so this actually takes linear time if you put it all together. And I'm sure that you're not satisfied with this type of complexity analysis. So I'm going to give you more details on this. So let's add it all up. So you can say, For n over 4 of the elements, I have to do one swap. For n over 8 of them, I have to do 2 swaps. For n over 16 of them, I have to do 3 swaps all the way down. For one of the elements, I have to do log n swaps. All right, what does this add up to? Here's an easy way to come up with this summation. You guys probably remember this from your math courses. So you could say, let's say total time t is equal to n over 4 times 1 plus n over 8 times 2 plus n over 16 times 3 plus ... And then easy way to simplify this is to say n over 2, I'm sorry, t over 2 is what? It's n over 8 times 1 plus n over 16 times 2 plus n over 32 times 3 plus ... And then you basically subtract t over 2 from t, and that would give you t over 2 equals 2. So this n over 8 cancels out with this 2. These two n over 16s, they cancel out with this 3, so there's only one n over 16 left, and so forth, right? So everything basically gets simplified to n over 4 plus n over 8 plus n over 16 plus ... And this is something that we should be very familiar with, and we should know what this summation is. Can you guys tell me what this all adds up to? All right, so what does this add up to? That's right. So all of this adds up to n over 2. So t over 2 is equal to n over 2, which means that t is equal to n, right? So you could basically say that the construction of the binary tree, so construction of a binary heap can be done in O of n. All right. So do you guys have any questions on this? Okay. If the data is coming in by dynamic, do you mean that if the data is coming in real time, like this is a basically an online solution? Yeah, of course. Yeah, real time. So in that case, you have to use the insert operation. So you don't really have all the elements to begin with. So of course, you have to do the insert one at a time. Yeah. So so you don't have this option at that time. But there are a lot of cases where we do have all the data. And so, for example, the algorithms that we're going to be looking at later on, we do have all the data ahead of time, and we can take advantage of this method of construction of the heap to save some time. All right. Do we need to perform two comparisons for n over 4? We're basically doing two comparisons, but only one swap, right? So we're only basically counting the number of swaps. We need to use insert operation. Yeah. Yeah, by swapping, I'm basically talking about moving an element down, moving the other element up, swapping them. Yeah, it's part of heap find, yes. All right. Why we need one swap at n over 4. Yeah, because you basically at n over 4, you need to compare the key value of this element to the key value of the children. So let's say the key value over here is, let's say 20, the key value for children, let's say it's 21 and 18, right? So if it's supposed to be, let's say, a max heap, right? So you have to check the key values to see which of these child elements. So you have to do two comparisons. Key value, compare the key value to the left child, to the right child, see if there's any one of them that has a higher key value, and then do a swap, right? But you only do one swap. Okay. You do two comparisons and okay, so here's a quick problem for you guys to solve. So we have an unsorted array of length n, and then we're looking for the top k values in this array. And k is, of course, less than n. And a couple of constraints that you've been given is that you can't use any other memory other than what we have been given in the array, and you have to find this solution, the top k values, in this time, O of n log k. So these are the two constraints. Okay, so think about how you can do this. Of course, we just talked about heaps, so you might think that that it would be useful to use heaps in this process. Yeah, so for the, somebody says for the complexity analysis, why are we not using the number of comparisons instead of number of swaps? Well, for each comparison, for each swap, we have to do at most two comparisons, right? So we can count the number of swaps, and if you multiply it by 2, if let's say number of swaps comes out to be n, right? So the number of comparisons will be 2n. So for our complexity analysis, it doesn't really matter whether we count swaps or we count comparisons, because in this particular case, the number of swaps and the number of comparisons are related to each other, right? All right, so there's one solution that that is suggested. Connor is suggesting you build a heap from the array. So how long would that take? So okay, so if you want to basically pop off the elements off the top of that heap, how long would that take? Each operation takes how long? That would be an extract. Well, no, it's an extract. It's an extract max, right? So extract max is going to take log n time. So you're going to do that k times. So it's k log n. And it takes you all of n time to actually construct it. So if you're looking for n log k, this means that you're basically using a different approach. right? So we're looking for something that gives us big O of n log k, right? So if you're creating a max heap of size k, then all right. So let's say we keep a heap of size k. Now, does that heap have to be a max heap or a min heap? A min heap. That's right. So you could say, all right, so these are my n elements. So this is an array of n elements, right? I can create a min heap of size k here, right? A min heap of size k. So how long does it take me to construct this heap? This takes O of k. That's right. Because you remember we can construct heaps in linear time. All right. And do we need any additional memory for this? No, because we just discussed a method of constructing the heap in place within the array without any additional memory. So this can be done. Now what do you do? Well, there are basically n minus k elements sitting out there that have to be tested to see if any one of them is greater than the smallest element within this set that I'm keeping in this heap. And if there is an element like that, then I want to put that element into the heap and take out the one that has the minimum value. So the useful thing about this min heap is that the smallest element is very accessible now. So the smallest element amongst these k elements is at the top and can be easily removed, right? So basically, you then basically run through the remaining n minus k elements. If any element is larger than, element at root of the heap, then replace it with element at the root. So how long would this take? So you have to do this operation n minus k times, and that's right, it takes n minus k times log k, right? Because the extract min, actually in this case, extract min operation takes log k, and the insert operation takes log k. So basically overall it takes n minus k log k time to perform that. Initially we actually had to do this. We know that this is O of n log k, right? All right. Why is extract min log k? So the extract min, you remember the extract min operation was basically logarithmic with respect to the size of the heap. So the size of the heap here is k. So So the extract min operation is going to take log k. Isn't it constant since it's a root? No, we're not talking about finding the element at the root. We're talking about extracting the element at the root. So when you're extracting an element at the root, you have to move things around. So it's not constant time, right? Okay. Very good. So one more thing before we leave binary heaps. How long do you think it would take us to merge two heaps of size n? So to merge two heaps of size n, two binary heaps, of course, I'm talking about. Yes, it would take O of n time. How would you do it? All right, so that's right. So the way you can do this in linear time is that you basically combine the two arrays. You basically concatenate them together. You create you grab memory of size 2n. You put these heaps into that array of size 2n. And then you just basically create a heap out of it, right? So you ignore the fact that these two arrays of size n contained heaps in them, right? So you just ignore that. You just basically move these two arrays of size n into an array of size 2n, and then build a heap in linear time. So this takes all of n time. All right. That is right. Okay. Very good. So a priority queue can be constructed using a binary heap. And we looked at the properties of a binary heap. It has very good storage requirements because you basically don't need any pointers to keep around. It's all stored in an array without any pointers. The cost of navigation through the binary tree is very good. So it has really nice properties. Now, there are some other heaps that, in terms of complexity, they sometimes have better complexities for some of these operations. So I want you guys to know about these heaps, not to the extent that we, studied the details of the operations for a binary heap, but it's good to be familiar with these other heaps and know about the complexity of the operations in these other heaps as well. So I want to switch over to okay, and talk about binomial heaps. There is basically two heaps that I want to talk about: binomial heaps and Fibonacci heaps. There's one question. Can you quickly reiterate the solution? Find the k smallest largest. Yeah. Yeah, so, all right, so let me go back to the other notes. All right, so what we did, we had an array of size n, okay, unsorted. We wanted to find the k largest elements. We constructed a heap of size k in the first k elements of the array, right? And that takes all of k time, right? So basically the smallest element is going to be sitting right here, the first element of that heap. That will contain the smallest element, right? And then you would go through. So once you're done with this heap, then you're going to go through the remaining n minus k elements and check the value of each element, compare it with the value of the element sitting at the root of the heap, which is the smallest one, and see if this one is larger or this one is larger. If the new element over here is larger, then replace it with the element at the top of the heap, right? So basically you keep putting in elements into this set of k elements, the elements that are larger than the smallest element in the set of k elements. So as you move through the whole rest of the array, you keep putting in the larger elements, and you take out the smallest element from the set of k elements, and that basically gives you the k largest elements in the heap. All right, k largest elements in the array, I should say. All right, okay, very good. Going back to the other notes. So you want to talk about binomial heaps and Fibonacci heaps. The reason I want to bring up binomial heaps is that in terms of the cost of operations, you'll see that they're not much better than the cost of operations in a binary heap, but since they're the basis on which Fibonacci heaps are constructed, so we're going to quickly get to know binomial heaps, and then we're going to take a look at Fibonacci heaps. And we're not going to spend too much time on Fibonacci heaps because you could spend a whole lot of time doing complexity analysis of various operations there. We don't want to do that, but we want to get to know them well enough so that we can use them in cases where it's appropriate. So similar to binary heaps that are constructed using binary trees, binomial heaps are constructed using binomial trees. Okay, so we're going to start with the definition of what a binomial tree looks like. So we say a binomial tree, B sub k, is an ordered tree. An ordered tree is a tree where the order of the siblings makes a difference, right? Defined recursively. So a binomial tree B sub 0 is just one node. And a binomial tree B sub k consists of two binomial trees, B sub k minus 1, that are linked together such that root of one is the leftmost child of the root of the other. So based on this definition, B sub 0 is just going to be like this, one node. B sub 1 is going to be two nodes, one being the leftmost child of the other. Then we have B sub 2, which is two B sub 1s, one of them leftmost child of the other, and B sub 3 would be two B sub 2s, one of them would be one b sub 2 is the leftmost child of the other. Do I need to go further? B sub 4. So this is 1 b sub 3, and so b sub 4 is 2 b sub 3s. So one of them is the leftmost child of the other, right? Okay. So so these are binomial trees. Now, if you look at these binomial trees, you'll see the binomial tree b sub 0 always has only one element in it. B sub 1 always has two elements in it. So if you were to create a binomial heap of an arbitrary size using binomial trees, then for a given size, it may not be enough to use one tree only. So if you want to use, for example, create a binomial tree of size 7, binomial heap of size 7, then you can't basically construct it with just one binomial tree. This one only has 4 in it, right? So you need one that has 4 in it, you need another one that has 2 in it, and you need another one that has 1 element in it. So you need to put binomial trees together to create a binomial heap of a certain size. Okay, so then we can say a binomial heap H is a set of binomial trees that satisfies the following property. So each binomial tree in H obeys the min heap property. We know the min heap property already from binary heaps. And for any non-negative integer k, there is at most one binomial tree in H whose root has degree k. So basically it says that you can't have two b sub k's in a given binomial heap. Right? All right. Okay, so let me just give you an example of what a All right, so this is just an example of what a binomial heap could look like. This is a binomial heap of size 7 and has a b sub 0, a b sub 1, and a b sub 2. And for example, you could see that this is, this is not an 8, because that would not make it a min heap. So you could see that this is a min heap, right? So each one of these trees, binomial trees, it's basically it satisfies the min heap property. But if you say that this is, for example, the head of the heap. This is the pointer to the head of the binomial heap. The minimum element is not right here, right at the head of the heap, right? So if you're looking for the minimum element, you actually have to search this root list to find out where it is. It could be in any one of those trees. So if you're basically looking at the performance of these operations, the find operation is going to take how long? How long do you think? All right, so how many trees are we gonna need to be able to store n elements. That's right. We're going to need at most log n trees. And where are we getting that from? Well, if you look at the number of elements that you have within each one of these binomial trees, you see that basically they correspond to the bit values in a binary number, right? So this is the rightmost bit, the first bit, second bit, third bit, and so forth, right? That's right. So how many bits do you need to store to basically represent a binary number? To represent a number in binary, you need, for number n, you basically need log n bits. So the same thing over here with binomial heaps. You need at most log n trees to represent a binomial heap of size n. Okay, so there is log n. There's at most log n trees over here. So the find operation takes O of log n, which is actually slower than the find operation in a binary heap, because the find operation there took constant time. How about the insert operation? Well, let's say I do an insert of this element into the heap that I just showed you up here. So what happens if I insert the element 9? Let's put this element 9 at the root. Seven, 10. All right. Okay. So if I just stick this new element 9 in the root list, would that work? Well, it's not going to work, because now I have two b sub zeros, right? And that violates the requirement that the binomial heap should not have two b sub k's, right? So what do I have to do here? I need to merge them to create a b sub 1. So we're going to get, one of the two heaps becomes the leftmost child of the root of the other. So if we're constructing a min heap, then 9 goes into the root list, and then 12 becomes the leftmost child of it. Okay, now again we have a new situation we need to deal with. Now we have two b sub 1s. Again, I have to merge them. All right, so this becomes, so 7 goes in here. All right, and remember, okay, over here, what we had was, what did we have there? 3, 5, 12, yeah. Okay, so we have 3, 5, 12, and what was it? 18. Now we have two b sub 2s. Finally, we have to merge these two to form a single binomial tree. All right. So how long does it take us to merge two heaps together to make one the leftmost child of the other? And you remember, now we're dealing with pointers here. So these trees are kept together using pointers. So to make one tree the leftmost child of the other, how long would that take? Constant time, right? So it's just a matter of moving some pointers around. Right? Okay, now how many of those merges do I have to do at most when I insert an element into the heap? We have to do log n, right? Because there's at most, there's going to be log n trees in this root list. And basically in the worst case, I have to combine all of them together, which takes log n merge operations. So the insert operation takes O of log n. So we're not going to go through the remaining operations like delete or extract min or decrease key and things like that. So I just want to give you a sort of a little table over here to remember things. So binary heap and a binomial heap. So it's very easy to remember for a binomial heap, pretty much all the operations, except for the construction of the heap, takes log n time, right? So find min, extract min, decrease key, delete, merge, construct, and should add important one here, insert and delete. I'm sorry, construct. So it's these we already know. Find min of 1. These were all of log n. Over here, this was merge was O of n here. This is O of log n, and this is O of n. For a binomial heap, it's very easy to remember. These are all log n, except for the construction, which is linear time. All right, so we're not really going to get into the details here because you'll see that the performance of these operations is not looking much better than that for a binary heap, except for the merge operation. So for the merge, you have to do O of n operations for a binary heap. For a binomial heap, you can actually do this in O of log n. Right? But aside from that, because the merge operation isn't a very popular operation to perform on a heap anyways. So the binomial heap doesn't have a lot of advantages over a binary heap. But the next thing that we want to talk about is Fibonacci heaps, which do have better performance than binomial heaps. But let me see. Why would you want to merge two heaps? There could be cases where you have to merge them. These are sort of general purpose data structures, and depending on what we want to do with the algorithm, you might want to merge two heaps together. I'm not sure. Where is binomial heap used then? Well, the reason why we talk about it is that they're the foundation for Fibonacci heaps. So I want to talk about Fibonacci heaps and show you a couple of things with that. And without really knowing how these binomial trees are constructed and what they mean, it's not going to be easy to talk about Fibonacci heaps. So that's why I'm just giving you a background on binomial heaps. Okay, now in a Fibonacci heap, we're getting some additional performance out of these operations, specifically for the insert operation and decrease key, and also find min. These operations, they all have better performances in a Fibonacci heap, and one way that we're gaining that performance is by procrastination. Right? So you see that when we're doing housekeeping in a binomial heap, for example, the moment you insert an element into the binomial heap, you want to make sure that you don't have two B sub k's, right? And that everything is stored in the proper format of having basically binomial trees, not repeating any binomial heaps of size k, binomial trees of size k. So every time that you put something into the heap or removing something from the heap, you're doing housekeeping to maintain that specific format, right? So every one of those operations is going to take time. Now, in a procrastination, the true way of the computer science, yeah, right? This is one of the few cases, guys, that procrastination really works. I don't want to make this sort of a teaching of a way of life. So, but this in this case for Fibonacci, it does actually work, where you don't immediately react to the changes in the in like adding an element into the heap or removing something into the heap. Well, removing something from the heap, yes, you react to, but when you're inserting things into the heap or doing decrease key operations, things like that, you're not really changing. You're not strictly doing full housekeeping for the whole data structure. So you kind of procrastinate on your housekeeping. Right. So for basically the organization, maintaining the organization of the heap with and strictly adhering to the rules that all the trees have to be proper binomial trees, and you cannot have 2b sub k's at any point in time in a binomial heap. To maintain that structure, I'm calling that housekeeping, right? So every time that you add an element into the heap or remove an element from the heap, you have to do some housekeeping, right? So you have to, for example, what we did over here, you have to merge all these trees of size b sub 0, b sub 1, b sub 2 into a single b sub 3, okay? To make sure that this is a properly maintained binomial heap. But in a In a Fibonacci heap, we kind of procrastinate on stuff. So you add in elements in there and you don't really care about doing that housekeeping. So then you end up with basically some mess that you have to clean up at some point, right? So when you actually get to do the cleanup, then that operation where you're performing all the cleanup, that cleanup looks expensive, right? Because you've basically procrastinated for some time, right? So that specific operation is going to be expensive, but you can't say that that type of operation is always going to be expensive, right? This is only expensive because you procrastinated for a long time. So if you look at the number of operations that you've procrastinated on and basically distribute the cost of this expensive operation over all those procrastinations, you'll see that the cost of this operation is not that much. So that basically brings us to the topic of amortized cost analysis. Okay. So before we talk about Fibonacci heaps, I want to talk about amortized cost analysis. So, are you with me, guys? We're taking another tangent. So we're already on a tangent talking about some data structures, but we're taking a second tangent now, talking about amortized cost analysis. We're going to come back to Fibonacci heaps, and then we're going to go back to greedy, right? Okay, so here's an example of where amortized cost analysis comes into the picture. Let's say you've developed some code that looks like this. You know, you've spent a lot of time on this code, developed this wonderful algorithm that uses a stack as the data structure. At each iteration of this algorithm, you're either performing a push operation or a pop operation. And we know the cost of push and cost of pop, right? We know push costs constant time, pop costs constant time as well. So you've done extensive complexity analysis on this algorithm, and you know that the worst case runtime of this algorithm would be what? Big O of N. Very good. Okay. Now, your research department tells you that they have a very powerful operation that they just developed on the stack, and they want you to try it out. So this operation is called multipop. It's a very powerful operation. It basically helps you pop all the elements off the top of the stack. So if you have n elements on the stack at this point, it pops all of them. Okay. So the multipop operation itself basically could take all of n time, right? So you're very excited about that. You go in and incorporate this multi-pop operation into your algorithm. So at every iteration, you're doing push or pop or multi-pop, right? Okay. So after a while that you're basically looking over your work, you think, well, what is this going to do to my complexity? You know, I worked really hard getting a linear time performance out of this algorithm. What is multipop doing to it? So we know that the worst case performance of push pop are 1. Worst case performance of multipop is O of n, right? And I'm doing all this in a loop. So what is the worst case performance of my algorithm now. This is O of. Yeah, if you just look at it like that, it's O of n squared now. You're doing O of n operations at most, at every iteration, so it's n squared, right? But is this a tight bound? So is this a tight bound? So it is true that it's O of n, right? Well, let's examine this. Let's examine this, right? One way to perform amortized cost analysis is through aggregate analysis. So in aggregate analysis, we say, well, let's think of a worst case scenario for a sequence of n operations, right? And then take the total time for these sequence of n operations. So these sequence of operations, they might include various operations. It doesn't have to be a single type of an operation. So you could have pushes, pops, multi-pops. So a sequence of n operations involving different operations, right? And let's say they take time t of n total, right? Then you're going to divide basically the total time t of n by n, and that would give you the amortized cost of all these operations, right? So the amortized cost is basically, in this case, the average cost of all of these operations, okay? So here's how we're going to apply the aggregate analysis to this particular example I gave you about the for loop and the stack. So we know that the multi-pop is going to take O of n time in the worst case, right? But that's when you have n elements pushed on top of the stack, right? So how do we actually get to n elements on the stack? So you must have basically n pushes, right? Because the stack, basically you're starting out with an empty stack, right? To get n elements on the stack that you could basically do a multi-pop on that takes O of n time, you have to have n pushes to get there, right? So it basically says you have a sequence, in the worst case, you have a sequence of n pushes and a subsequent multi-pop, right? So this is actually n plus 1 operations, right? Okay. So how long would this take? It's n pushes, which is O of n time, plus a multi-pop, which is another O of n. So the whole time t of n is O of n, right? So now we just basically compute the amortized cost. We amortize the cost of these n operations, and we get an amortized cost, or an average cost in this case, of O of n divided by n, which is O of 1. Okay, so we can say that the amortized cost of push and pop and multi-pop, they're all basically O of 1. Okay, so now if you're doing complexity analysis on this piece of code, you could, instead of using worst case performance of these worst case costs of these operations, you could use amortized cost of these operations to get a better bound on the performance. So you can say this is O of 1, this is O of 1, this is also O of 1. So the complexity would be O of n. Okay, and this O of n is not the average performance of this code, right? It's the worst case performance of worst case cost of this whole algorithm, right? Which is O of n. These costs, the cost of the operations, are average costs. But when you're plugging in the average cost of the operations into this loop, then you're actually coming up with the worst case cost of the overall algorithm. So I want you guys to make this distinction between average cost of an operation and the worst case cost of the actual algorithm that uses those operations. All right. So here you see that the runtime is actually O of n, which is a type bound, right? So we are actually doing n loops here. Okay, any questions on this? There's another method that I want to show you guys too, but before we go there, any questions on aggregate analysis? Okay. Yeah. All right. So basically, we're trying to find a worst case sequence of n operations. Well, we know that the worst case scenario for a multi-pop is to have n elements in the stack, right? That you have to pop. In order to have n elements on the stack, what do you have to do to get there? You have to have n pushes, right? So the worst case sequence of n operations becomes doing n pushes on the stack, followed by a multi-pop, right? So then basically you get O of n of push, O of n for multi-pop, you add it up together. All right. Okay. So there's another method that you could also use. It's called the accounting method. There's yet another method, the third method, the potential method that I'm not going to go through. But if you want to go through that third method, you're welcome to do that. It's in Corman, but I don't want to get into that because it's not going to be very useful for us. Anyways, the accounting method goes like this. That we basically assign some charges. It's up to us how much we want to charge an operation. Right? So you basically charge different operations as you see fit. Basically, it's up to you how much you want to charge them. And then what you need to do is that you need to keep track of the cost of the operations and the charge of the operations. If basically an operation is charged more than its actual cost, then you have some credit that you can store in the bank, right? And if you have credit in the bank, when an expensive operation comes along, you could actually pay for the cost of that operation. If it can't be covered by the charge of that operation itself, you can actually use the credit that you have in the bank to pay for it. And what you just need to make sure is that your credit in the bank never falls below zero. So if you basically, if you can guarantee that in any sequence of operations on the data structure, your credit never goes below zero with the given charges, then you can say that these charges are your amortized cost. Okay. So I'm going to give you an example. Again, going back to this code. Okay, good question. Amortized cost analysis is with respect to operations on a data structure. It's never about the overall cost of the algorithm, right? So it does affect the cost of the algorithm, but we're not talking about the algorithm taking an amortized cost of something. The operations on a data structure have amortized costs associated with them. But when we're doing complexity analysis on an algorithm, we're not using amortized cost for the complexity of the algorithm. Do you see the difference? All right. Okay, so how do we calculate amortized cost at any time? So let me go through this, Connor. Let me go through the explanation here, and then if you still have that question, I will go to it. So here's the loop again. All right. So we have this loop, and we want to do basically amortized cost analysis using this other accounting method. So to just basically start out as and this is more of a trial and error, this amortized cost analysis, because the charges are up to us. And initially, you may not know how much you want to charge each operation. So let's start with a charge of 1 for each operation: push, pop, and multi-pop. Okay, so the charge for each operation is, let's say 1, right? So you charge push 1, and let's say you have 2 pushes and then a multi-pop, right? So this is a sequence of we're looking at a sequence of 2 pushes and a multi-pop. So the first operation, push, you have a charge of 1, and it actually costs 1 to do that push. So nothing is stored in the bank. You don't have any extra charges that you could put in the bank, right? So the bank is zero balance. The push, next push comes in. Again, actual cost is 1, so it uses up the charge, right, to pay for the operation itself. And then still your account is at 0. Now a multi-pop comes. The multi-pop also is charged 1 unit, but the cost of the multi-pop is actually 2, right? Because you have 2 elements in the stack that you have to pop, right? Each one has a cost of 1. So now you end up with a negative credit in the bank. So this basically tells us that these charges are not sufficient to take care of the worst case performance of a sequence of n operations. Okay. So based on this sequence that you just see, 2 pushes and a multi-pop, which of these operations do you actually have to charge more to build credit in the bank? Do you have to charge push more, or do you have to charge multi-pop more? Yeah, so, well, multi-pop is going to cost more, but who do you charge? That's right, you charge push more so that you actually put credit in the bank so that when a costly operation like multi-pop comes along, you can use that credit that you built in the bank. All right. So does actual cost refer to the number of elements that are affected by the operation? No, the cost is actually the cost of the of that operation itself. Well, so you basically have to so a push, you have to move an element on the top of the stack and let's say change the pointer on the stack. So that basically takes 1 unit of cost to perform that operation. Okay. All right. So here's try number 2. So now we're going to say, I'm going to charge push 2 units, and then for pop and multi-pop, I'm not even going to charge them. The charges are going to be 0. Right? So let's see what happens when we have a sequence of 2 pushes followed by a multi-pop. Okay, so the first operation is first push, you charge it 2 units. The actual cost is 1. You build 1 unit of credit in the bank. The second push comes along, you build another unit of credit in the bank. So now you have 2 units of credit in the bank. Now the multi-pop comes along, you charge it 0 units. The actual cost is 2, but you basically have 2 units stored away in the bank that you could use to pay for this credit, so your credit goes down to 0. Okay. So this means that you can actually use these these charges to come up with amortized costs for these operations. So this tells me this is basically constant time. This could be 3 or 4 or whatever. This is still all of 1. This is all of 1. This is all of 1. So basically, this tells me that that all these costs are the amortized costs are constant time. Okay. Now, in this method, you're not always going to end up with constant times, of course, for the operation. So, maybe the amortized costs of an operation comes to be log n, or comes to be O of n, or O of n squared even, right? So amortized costs are not always constant time, right? So in this case, though, it turns out that the amortized costs are coming out to be constant time. So again, you take those amortized costs, plug it into this, and you get a worst case performance of this algorithm to be O of n. Well, the end goal is to come up with a more realistic cost of the overall cost of the operations of a data structure. So when you look at the operations of a data structure for the example that I gave you with the Fibonacci heap and procrastination, there are certain operations that cost a lot, right? But if you take the worst case cost of that operation and multiply it by how many times that operation is performed within a loop, that is not going to give you a tight bound on the overall cost of the algorithm, right? So if you can find an amortized or average cost of that operation, that is going to be basically helping us in coming up with a more realistic and more a tighter upper bound on the performance of the algorithm. Okay. Okay, so with the amortized cost, like I said, it's trial and error. You try to assign some charges to the operations, and you see if this works out or not, right? And so we're saying that you remember the worst case sequence of operations where multi-pop costs a lot is when you do a whole bunch of pushes and then a multi-pop, right? So that's the worst case. So we're looking at that worst case. We're saying, okay, let's do pushes and then a multi-pop. What should I be charging these pushes? What should I be charging multi-pop for the sequence, so that my credit never falls below zero? So that's the intent with the accounting method. So we're going to start with some guesses. Let's say we charge each one of these operations 1 unit, right? But if you charge them 1 unit, the charge is only enough to pay for their actual costs, and nothing gets stored in the bank. So when a costly operation like multi-pop comes around, there's no credit in the bank to pay for it. Okay, so what we do is to charge the operations that the push operations that basically the repeated many times before that costly operation pops up. So what you're doing is basically spreading the cost of that costly operation on those other operations that build to that moment, right? So you're charging the pushes more, so you're charging push operations 2 in your second try, right? And by doing that, you're building some credit in the bank. So the cost of the operation is only 1, you charge it 2 units. So every time you do a push, more credit goes into the bank. So then the number of operations in a multi-pop is directly related to how many elements you pushed on top of the stack. So if you have n elements on top of the stack, it basically means that you've done n pushes and you've put in n units of credit in the bank that now you could use to pay for the multi-pop. Yeah, so yeah, you could do that. This is charging is up to you. So you could charge them, 20 units and then have lots of credit in the bank. But when we're doing amortized cost analysis, we want to be able to do with as little charge as possible, so basically we're finding the best average costs or the best amortized cost for the operations. You can always overcharge and have extra credit in the bank, right? But you're trying to keep the charges as small as possible. So that's basically where the trial and error comes in. Okay. Okay, why build up credit and not directly charge the operation to its equivalent? Well, if you don't put any credit in the bank in this accounting method, when multi-pop comes around, then basically you have to charge it n units, right? Because there could be n elements sitting on top of the stack. And you remember, these charges are going to be our amortized costs, right? So if you do it that way, then your charge is basically the amortized cost becomes O of n, right? And that's actually what we wanted to overcome, right? It's the use of accounting method to help you achieve more accuracy in assessing costs. Well, it's just one other way of coming up with the amortized cost. So whichever way, sometimes it's easier to do the accounting method. Sometimes it may be easier to do the aggregate method. So I want you guys to know both so that you have a choice. All right. So let's see. All right. So I think this is a very good point to take a little break. Let's take a 10-minute break. We'll come back and start at 3:37. All right. See you guys soon. All right. So now we're back, and we know what amortized cost analysis is. We're back one level of the tangents, right? Back to a discussion on heaps. So let's look at Fibonacci heaps. We don't want to, again, we don't want to get really into the details of all these operations in a Fibonacci, but to give you an overall picture of it, they're loosely based on binomial heaps. And we say that a Fibonacci heap is a collection of min heap trees, but these trees, they're not constrained to be binomial heaps, binomial trees all the time, and like the binomial trees, they don't have to be ordered, so it's more relaxed basically. So let me just show you an animation of the heap, because I think it's the easiest to actually look at an animation here. So let's see. Can you guys see my screen here? Let's see. All right, very good. So I'm going to do, let's say, a number of insert operations. So first element, second element. So we're constructing a min heap. And you see that when I'm inserting elements into this heap, they just get added to the root list. And that the data structure is keeping track of the element with the minimum key value. So if I entered an element, let's say 5, now this element has the smallest key value, so the pointer to the head of the heap is pointing to this element with the smallest key value. 24. But you see, I'm not trying to maintain the heap in a way that we have basically a properly structured set of binomial heaps, and you don't have repeated b sub k's. So all of these are b sub zeros, right? So I keep entering elements, and they keep going into the root list. Okay, so so this is all procrastination, basically. Now, when you do a delete operation, that's when you cannot keep this mess going on anymore, and you have to do some bookkeeping. So now we're getting to an operation where this operation has to take basically care of all the mess that we created. And this is an expensive operation now because it had to do all this bookkeeping, right? But if you look at the amortized cost of this operation, if you amortize it over all those insert operations that went into the data structure to get to this point, you see that the cost of the operation is not, the amortized cost is not that much. It actually turns out to be log n, right? If you amortize the cost. Right, but again, if you insert more elements into the heap, again, you keep procrastinating, right? Again, and if you do a remove, then again, you have to deal with the mess, and you do housekeeping, and that operation again takes more time. right? And depending on how much procrastination you did, you will end up with, more or less work. All right. I'm not also showing you all the pointers. Let me just show you for a moment all the pointers involved. There is a whole bunch of pointers involved in maintaining a Fibonacci heap. So the root list is basically a doubly linked circular linked list, and then you have pointers from children to the parent, from parent to some children to the leftmost child. The siblings have pointers to one another. So there's a lot of pointers that you have to basically maintain. So those constant signs that are involved in maintaining these pointers, they're also pretty high, and you have to basically store a lot of pointers too with this data structure. So if memory is an issue, then might want to reconsider using the data structure like that. All right, so let's go back here. All right, so now we can talk about these costs for all these different implementations of a priority queue. If a priority queue is implemented using a binary heap or binomial heap, we've seen these numbers before. I've added Fibonacci heaps in the third column over here. So you see that the amortized costs. So these are amortized costs for a Fibonacci heap. So this is constant time to do a find min, because you remember the element that you're pointing to as the head of the heap actually stores the smallest element, and then insert takes constant time. The amortized cost of extract min and delete are log n, and these are really the only two costly operations. The other operations, decrease key, even merge, takes constant time for a Fibonacci heap. And the construction also takes linear time. So now you see that compared to a binary heap, you actually do get better performance, especially if you have an algorithm that does a lot of decrease key operations. And there are algorithms like that where you have to do a decrease or increase key operations a lot. You see that it has an amortized cost of 1. Also, the insert operation, has an amortized cost of 1. All right. So now this concludes our discussion of heaps. We're not going to get too much into those, as I said, into the operations and cost analysis for the different operations in a Fibonacci heap. That takes a long time, but all I basically want you guys to take away from this is that the Fibonacci heap has more attractive amortized costs, and it may be suitable for use in some algorithms where you do a lot of these operations that have constant time in Fibonacci heap compared to log n time in a binary heap. Okay, so let's talk about this algorithm that we've been preparing for. This is going to be a shortest path algorithm. We've already seen how we can solve the shortest path problem in an unweighted graph. So do you guys remember what we used for shortest path in an unweighted graph? BFS, that's right. So if the graph is not weighted, BFS would do the job. So, so now we're going to look at a more general graph. Given G with weights all greater than 0, so the weights on the edges all greater than or equal to 0. Find the shortest path from S to V, well, S in the set V, to V minus S. Actually, let me rewrite this to V minus S because this looked like it was the capital S, and this is supposed to be the little s. Okay. So we're trying to find the shortest path from a single point in the graph to all the points in the graph. Sometimes you're just interested in going, finding the path, the shortest path from A to B. The same algorithm would be used there. Similar to how BFS worked with finding a path between 2 points or finding nodes that can be reached from a starting point, and it had the same complexity. Finding the shortest path to all the nodes in the graph from a starting point, and finding a path from A to B in the graph using this algorithm, they both have the same worst case complexity. Okay. All right, so we're going to be using, of course, the greedy technique to solve this problem. So let's look at this this example. Let's say we're starting from S and we're trying to find the shortest path from S to all the points in the graph. So, and you're thinking greedy, right? So you have greedy on your mind and you want to move from S to some other point and find the shortest path. Where would you go? Y would be a good choice, right? So we're thinking greedy, so we're saying, well, I want the shortest path, so I'm going to go on the lowest cost edge out of S, and I'm going to land on Y. So when you get to Y, can you claim that you already found the shortest path to Y? Or is it possible that there's another path that goes around some other nodes and comes back to Y that's shorter? Yes, okay. So let me go back to the problem statement again. I'm going to highlight this assumption here, right? We said that the edge costs are all positive, right? So with that in mind, if the edge costs are always positive, can you go back here and tell me if it is possible for us to go from S through some other nodes and then come back to Y at a lower cost than phi? Is that possible? No, it's not possible now, because if you go from S to any other node that has a higher cost to get to than Y, you've already paid more than going directly to Y, right? And because the edge costs are all positive, then there's no way to make that make up for it, right? So you can actually declare that I found the shortest path to Y. Once you get to Y, you can actually say this is the shortest path to Y, right? So this algorithm that we're gonna talk about, it only works if the edge costs are positive. If you have negative edge costs in the graph, then this algorithm is not made for it. Okay. All right. So, okay. So now we got to y. Now what next? Do I then look at the neighbors of y, or do I keep going to the the other neighbors of s? So how do I proceed from there? Because right now we know how to find the shortest path to s's closest neighbor, but how do we generalize this greedy algorithm? How do we generalize this? Well, you remember, coming up with greedy solutions, it was trial and error. So you might say, well, let's go and look at the closest neighbors to y, or the next closest neighbor to s. So you could try these things, and you'll see that you'll find counterexamples. So what you'll end up with is that basically the right approach is that once you find a set of nodes, the shortest path to a set of nodes, you could put them into a set, right? Let's call this set big S, right? And then the way you find the next node that you want to find the shortest path to is to look at all the other nodes in the set that you call, basically all the other nodes are going to be in the set V minus S. And you're going to pick the nodes in the set V minus S that currently has the shortest distance from S, from the starting point S. Okay? So it could be a neighbor of Y, it could be a neighbor of S in this case. Or in general, it could be a direct neighbor of any of the points in the set S. But it has to be a direct neighbor of one of the points in the set S, right? It could be any one of the points in the set S. So then you'll find that node, and you say, okay, I have the shortest distance to that node, and then you bring that into the set S. Right? Okay, so this is basically the high level algorithm. You start with a set S of vertices whose final shortest path we already know. Of course, there's always the starting point S, because you know the shortest path from S to S is there's basically a path of length 0, of cost 0. From S to S. And then at each step, you find a vertex U in the set V minus S with the shortest distance from S. And then you add it and repeat. All right. Okay, so let's go through this algorithm in step by step. In all basically go over all the details and really understand this well. So initially what we do is that if you have a starting point S, you assign a distance of 0 from S to itself, and you assign a distance of infinite to all the other nodes. And then you basically put all of these nodes in a data structure. So including S, everything is in a data structure. And these key values, the key values associated with these nodes, are their distances from S. Okay. So in the first step, in the first iteration, you take the element or the node in this data structure, which has the lowest key value, right? And that would be S, right? And you put S in the set S. So initially, S1 would include this node S itself, right? So you have S in the set S, and everything else, all the other nodes are in the set V minus S. Okay. Now, after you basically bring this node in the set S, then you examine the neighbors, the immediate neighbors of the node that you just found, and you see if there is a faster way to get there using the node that you just found. Okay, so you look at the immediate neighbors of S and you say, okay, can I get there faster through this node? So you examine Y and say, yes, of course, I can get there faster. I can get there at a cost of 5, because 0 plus 5, that gives me 5. And you look at T, say, yeah, I can get there faster at a cost of, nope, not 5, at a cost of 10. Okay. So, so there's a question there, visit neighbors of Y with edge waves. Okay, fine. Okay, I'll come back to the questions later on. All right, so basically once you find a node in a given iteration, you go through its neighbors and you see if you get there faster than their current distance from S. And this step of going through the neighbors is called the relaxation step in the algorithm, and you perform that at every iteration. So the next thing is to now look at the key values. So you look at the data structure and see which element has the lowest key value and pick that node next. So if you're looking at the key values amongst Y, Z, X, and T, you see Y has the lowest key value. So in the second iteration, you're going to bring Y into the set S. Oops. So now Y comes into the set S, and now we're going to go through the relaxation step. Look at the immediate neighbors of Y and see how fast if we can get there faster. So you look at Z and you say, yes, I can get there faster. What should this be? 7. That's right. Because you can get there to Y with a cost of 5 and add 2 to it. You can get there at a cost of 7. And then for X, this should be 14. And for T, can you get there faster than 10? Yep, you can get there faster, cost of 8. Very good. So relaxation step is complete. Now you look at the remaining nodes in the set V minus S, consisting of Z, T, and X. So which one do you pick next? You pick Z. That's right. So then you bring Z into the set S, and you say that S3 is S, Y, and Z. All right. And now you go through the relaxation step again. And okay, you check the neighbor, immediate neighbors of Z. Can you get to X faster? Yep, this is 7 plus 6. That would give us 13. Anything else? Nope, I don't have to go back to S because I already know the shortest distance from S to S. So we're done here. Okay, so the next step is looking at T and X and picking the one that has the shortest distance, currently shortest distance from S, and that would be T. All right, so the next step, S4, S, Y, Z, and T, and so now this, all of this is the set S, and the only node in the set V minus S is X. If you perform the relaxation step on T, the only neighbor you have to visit is X, and you can get there. That's right, cost of 9. Okay. And the last step is that you basically bring X into the set. So S5, S, Y, Z, T, and X. And at this point, basically, we've found all the shortest paths from S to all the nodes. Or did we? So can you guys tell me if we found all the shortest paths from S to all the nodes in the graph? Well, yeah, I think I'm being very specific with the wording of the question. So, what is the definition of a path? A path is what? It's a sequence of edges that take you from one node in the graph to another node in the graph, right? So that's right. We only found shortest distances. We didn't find shortest paths, right? So can you take a look at this algorithm that we just described and tell me how you could modify this to also find all the shortest paths, not just the shortest distances, but shortest paths. Very good. So as soon as you find a new node, as soon as you find the shortest path to a new node, just remember who gave you, which parent node gave you that shortest distance. That's basically how that node was found. So if you just keep one pointer back to the parent node, then you'll have all the shortest distances. So for example, let me use a different color here. So you remember we found Y directly from S. So Y is going to have a pointer, keep a pointer back to S. This was a parent node that where this shortest distance was found. Z was found through Y, right? Because it has a distance of 7, it was 2 plus 7, right? So Z is going to keep a pointer back to Y, and T is going to keep a pointer back to what? T is going to keep a pointer back to Y. That's correct. So there's a pointer back to Y, and X is going to keep a pointer back to back to T, right? That's right. So now you see that we now have all the shortest paths as well. So we only need one pointer to keep around, right? Of course, these are not directly shortest paths because the arrows have to be flipped around. But you can see that if you keep these pointers, you can always find the shortest paths by flipping these edges in the opposite direction. You have the shortest paths from S to all the nodes in the graph. Okay. Yes, that's right. So good question. So this is called Dijkstra's algorithm for shortest path, and we should remember these algorithms by name because in homework or exams we basically refer to these algorithms by name. So you should remember these algorithms by name. It's these algorithms, shortest paths are definitely very useful in networks. We're going to talk about some other algorithms, shortest path algorithms that will also be useful, even more useful in networks. Okay. So proof of correctness. We're gonna basically do a proof of correctness on Dijkstra's using mathematical induction. So what we want to prove is that at each step, Dijkstra's finds the shortest path to a new node in the graph, right? And this is proven by mathematical induction. So as the base case, what does our algorithm pick as the first node to which we have the shortest distance? Well, it picks S itself, right? Because the shortest distance from S to S is set to 0 as an initial condition. And all the other nodes have a distance of infinite from S, right? So the base case basically involves the single node S, and it finds S correctly. So the base case is checked. Right? Now, inductive step. We assume that the claim holds for S when it's of size K, and then we take one more step and we say, okay, now Dijkstra's is going to take one more step, and S is going to have a size of K plus 1. Okay, so we're assuming that this claim that Dijkstra's basically finds all the shortest distances to the new nodes at every iteration. It holds for the size K, and then we go one more step, and we then have to prove that it also holds for the K plus first step. So at the kth step, so this is the S, we have basically S of size K in this set. And then let's say we find a new node. Let's call this node V, right? Let's say this is node V, and it's found at step K plus 1 in Dijkstra's. Now you remember, when we find a new node in the set V minus S, we keep a pointer back to the parent that gave us that shortest distance from S. So let's say that parent happens to be U, and that parent must be in the set S itself. So there is an edge that goes from U to V, right? So we're saying that we've already found the shortest distance from S to U, and as part of our assumption, the inductive hypothesis, is that Dijkstra's has correctly found the shortest distance from S to U. And now in this iteration, we found V as the next node to which we have found the shortest distance. And so this whole path, P sub U, going from S to U, plus this edge UV, we're claiming that that's going to be the shortest path from S to V. Okay. This is going to be proven by contradiction. So you could say, well, if this is not the shortest path, then there must be another path that goes from S to V that's shorter than P sub U plus UV, right? Now, this path also has to cross the boundary between S and V minus S at some point, right? Because V is outside of the set S. So we're going to focus on that edge that crosses the boundary. So let's say this is the edge on the path that crosses the boundary. We're going to call this U prime, V prime. All right. Now, can you guys tell me which of these distances is shorter? The distance from S to V prime or the distance from S to V? Which one is shorter? If we assume that Dijkstra's has worked properly so far, it must be that the distance from S to V is shorter than the distance from S to V prime, right? Because remember, Dijkstra's picks the node V as the next node. And how does Dijkstra's choose that node from all the nodes in the set V minus S? It looks at all their current distances from S. And we have the current distance from S to V prime, right? Through U prime, because we've found the shortest distance properly to U prime. That's part of our assumption, that we know the shortest distance to U prime, and we know the distance between U prime to V prime. So at this point, we know the distance between S and V prime, right? But we picked V as the next node, which means that the distance from S to V is shorter than the distance from S to V prime, right? Now, is it possible that by going from V prime to V, that we make up for that difference? Is that possible? That it's not, because the weights, exactly because the weights are all positive, right? See, for the proof of this algorithm, we're completely relying on the fact that we're dealing with positive cost edges. If we don't have positive cost edges, you cannot basically go through this proof, right? So this algorithm only really works for graphs that have positive cost edges. Okay, so since all the edges have positive cost, then going from V prime to V only adds to the cost of the path going from S to V through V prime, right? So that basically contradicts the fact that we're saying that going through V prime, we're going to get a shorter path from S to V. Okay. Okay, any questions on this proof? So this proof basically told us that at every step, Dijkstra's is going to find the shortest path to a new node in the graph. So it basically means that it finds the shortest path to all the nodes that it can reach in the graph. Okay. So, so we completed the proof. The next step is to do complexity analysis. So initially we say the set S contains the starting point, all the other nodes have a cost of infinite from the starting point. And then we go into this loop, this while loop, and as long as we have not found all the nodes, we keep going. So we select a new node from the set V minus S, which has at least one edge from the set S, and where the distance from S to that node is the minimum of all the distances from S to any node in the set V minus S. And then we add this to the set S. And then we have to go through the relaxation step. So this is very high level. This is a very high level algorithm. It doesn't give you all the details about relaxation step and so forth. But just wanted you guys to see this and tell me what data structure you think is going to be suitable to keep the nodes in. Because remember, the data structure that we need to basically build should allow us to put all the nodes with their key values in there, and at every point give us fast access to the element with the lowest key value, and also allow us to change the key values. You remember the relaxation step requires a decrease key operation? Very good. So we need a priority queue. That's right, a priority queue. And it was lucky that we just talked about that data structure and its implementations using binary heap and Fibonacci heap and all that stuff. Great. So now we can look at the implementation of Dijkstra's using a priority queue. So initially we we create a priority queue. Let's call it Q, with all the nodes having a distance of infinite from S, and V sub S having a distance of 0 from itself. Then we go into this while loop, and using the operations of a priority queue, the operations that we know of, we can do an extract min to find the next element to which we have the shortest path. So V is going to be the next node from the set V minus S, right? So extract min, and then add this to the set S. So yeah, you don't read this as SUV, right? So this basically says add the node V to the set S, right? Okay, and then then we jump into this loop, which performs the relaxation step. So for all the nodes that are neighbors of this newfound node V, we're going to check their current distance from S against the distance through V, which is D sub V plus L sub E. L sub E is just the cost of that last edge that goes between V and U. Okay. So we compare the two, and if this new cost, D sub V plus L sub E, is less than D sub U, then we do a decrease key operation. We set the new distance of node U from S to D sub V plus L sub E. And that's it. So loop over this, go back to the top of the while loop, and this will find us all the shortest distances. And of course, if you want to keep track of the paths, you have to put some code in there to keep track of the pointers. All right. So what is how long does this take to run? What is the complexity of Dijkstra's algorithm? So we have a few things to look at. We have the initialization of the priority queue, and we have the extract min operations, and we have the decrease key operations. Okay. So initializing the priority queue, this is going to take O of n. And you remember, this is independent of whether we are using a binomial heap or a Fibonacci heap or a binary heap, right? All of them basically take linear time for construction. So what is the maximum number of extract min operations that we need to perform? So how many extract mins do we do? That's right. So we have n extract mins. And how many decrease key operations do we do? So this outer loop goes O of n times. How many times do we do the inner loop, the for loop, in the worst case? How many neighbors could you have so that maximum degree can be n? So you could say, yeah, you do O of n squared decrease key operations, right? But there's actually a different way to look at this to bring that number down a little bit. So if you look at basically how you're going through the whole graph, you're only visiting the neighbors of V once. Right, so when you do an extract min of this node V, that's the only time that you do the relaxation step on the neighbors of V. Right? So how do you get to the neighbors of V? Through the edges that go from V to the neighbors, right? So how many times are we looking at each one of those edges when we're doing the relaxation step? Well, you're only looking at those edges going out of V once, right? Now, do you ever come back to V? No, you never come back to V, right? So during the entire execution of the algorithm, you're looking at these edges only once per decrease key operation, right? So one look at the edge, one decrease key operation. You don't look at these edges twice. All right. So in the worst case, you could actually do m, which is the number of edges, decrease key operations, right? So the number of decrease key operations, you could say it's O of n squared, yes, but it's not, again, a type bound. So you do order m decrease key operations. So if you put all of this together, what do we get? Okay, so let's see. You have n extract min operations, and you have m decrease key operations. So for a binary heap, you remember extract min and decrease key, they both cost log n, right? So this is n log n, this is m log n, and say the total if you basically add these up, if we assume that this is a connected graph, where m is at least going to be equal to n, we can simplify this to m log n. All right. For binomial heap, you remember all of these operations take log n time. So this would be O of n log n, O of m log n. So no difference. This is O of m log n as well. How about the Fibonacci heap? Does anything change here? So remember, the amortized cost of extract min, which is a delete operation, is log n. So this is n log n. So what is the amortized cost of decrease key in Fibonacci heap? That's right, it's O of 1, it's constant time. So this would be O of m. So what does this add up to? This adds up to O of, we don't know which one of these two is going to be higher, right? So the way we use the big O notation, when we don't know which of these functions is going to grow faster, we just add them together. So we're going to say O of m plus m log n, right? Okay. All right, so when you're comparing these performances to one another, which one do you think is a winner? Well, it's not yet clearly obvious if we have a winner, because it may really depend on the characteristics of the graph that we're dealing with. So let's look at two types of graphs. Let's look at a very sparse graph. In a sparse graph, we have very few edges with respect to the number of nodes. So you could say that m is O of n, right? We have very little connectivity in the graph. So you might have, like for example, a tree is a very sparse graph, right? So you could say if you simplify m to O of n for a very sparse graph, you end up with what? This would be O of n log n, right? And this would also be O of n log n. And what would this be? This would also be O of n log n. So if you have a sparse graph, then it doesn't really, in terms of complexity, these three implementations are going to be identical, right? You might as well use a binary heap because you don't have to keep around any pointers, and so the overhead is made maybe smaller than the other heaps. But what happens if you go to a very dense graph? So if you have a very dense graph, then m could be as high as what? N squared, right? So you plug in n squared instead of m here, so you're going to get O of n squared log n. this would be, again, O of n squared log n. And what would this be over here? That's right, O of n squared. All right, so now you see that there's a difference. And this difference is really associated with what? This over here, this term. Yeah. So you see that this the decrease key operations take O of m log n in binary and binomial heap implementations, but in a Fibonacci heap, decrease key operations take O of m times. So that's basically the advantage that the Fibonacci heap gives us here. All right. But again, this is not always the case that even if you have a Fibonacci heap, I'm sorry, if you have a dense graph, it doesn't mean that you always need a Fibonacci heap implementation of the priority queue, because you could have situations where you have, remember, the cutoff point, right? So you might think that a Fibonacci heap might help you over here, but it may be that for even when the graph is dense, for smaller problem sizes, maybe on this side, you're going to prefer a binary heap. All right. Okay, guys, any general questions about Dijkstra's? About the complexity or proof? Perfect. No questions. Whoops. Why is binary heap faster? Because it also has O of n log n. Why is binary heap faster? What in this case are you talking about? In the picture that I'm showing? I'm showing this picture because you remember there's a lot of constants involved in the actual cost of the operations. Like for example, the overhead associated with moving pointers around and things like that, that they're not going to show up in the complexity in the asymptotic notation, but those constants make a difference in terms of the actual cost of the algorithm. Okay. So for one algorithm, you might have, so let's say this could be in actuality, this could be, let's say 15n squared, and this could be 2n squared log n, because the constants are not showing up in the asymptotic notation. There could be some problems where this number is still less than this number, right? So when we're just looking at the asymptotic notation, we don't really know the actual cost of these algorithms, because we're omitting these constants. All right, so let's see. So for the proof, could you go over the contradiction part again? Yeah, no problem. So we basically assume that we've found the shortest path to k nodes in the set properly, and then we want to go to the k plus first node, right? So at this step, we're saying that we know the parent of V, which is U, is in the set S, gave the shortest distance P sub U plus UV to this node V. Right? Now, if there's a shorter path going from S to V, it must cross the boundary of S and V minus S at some point. Okay. Now we're going to focus in on the edge that crosses that boundary. We're going to call that edge U prime V prime. And we're going to ask the question, which distance is shorter, from S to V or S to V prime? Based on our assumption, we have properly basically found all the shortest distances from S to all the points in the set S, right? So based on that assumption, we know that at that moment where we're finding V, the distance from S to V is shorter than the distance from S to V prime because Dijkstra's is picking V. Okay. So then, since we know that the edge costs are all positive, there's no way for this path that has an additional segment going from V prime to V to be any shorter than the path through U to V. Right, because we already know that the distance from S to V prime is greater than the distance from S to V. So by adding some other positive cost to it, it can never be shorter than the distance from S to V. Okay. Now, in an industry setting, would you recommend sticking with a Fibonacci heap, even if for smaller graphs to account for potential future growth? Or would you say it's better to stick with a binary heap? Well, if you're dealing with a problem, I mean, if you have the choice of using different implementations of a binary, of a priority queue, depending on what your problem size is, then you could basically make that decision on the fly, right? If you have both implementations available, you could basically make that decision on the fly and use this or that. But of course, you have to have some information about how efficiently these data structures run on those particular machines, because it's not just a matter of these asymptotic, basically, complexities. You remember we talked about the constants involved. You remember there's machine performances are involved. So if you have some data that you could rely on for these data structures, how they basically perform on that particular machine that you're running, I think that would be the best way to decide which way to go on these data structures. And you also might have to take into consideration the memory usage. Do we have a systematic way to analyze the constants? Well, you could only analyze the constants once you actually have the implementation in front of you, the detailed code in front of you. And we don't really usually we don't do that, the systematic analysis of actual cost of the operations, because when you have an implementation, it would be actually easier to run the code and get some data points, right? To find out what those constants are. Right, so the actual number of operations, we actually don't spend time to find the actual number of operations when we're looking at that code. All right. So let's see what's next. Okay, so here's a new problem. We're not going to be able to go through the entire problem with all just like 7 minutes remaining, but I want to introduce the problem to you guys, and then tomorrow we're going to continue on this and finish it up. So you've been given a set of points. These are a set of points basically. And you're asked to build a network on top of these points, these locations. And somebody has already done some analysis, and told you that, for example, this connection over here doesn't make sense. It's too costly. So we already know that certain connections are not. Basically, we're not interested in that. We're given a subset of the edges. For example, this is a possible connection that we could use to build the network. And so these edges that you see here, these are the possible connections that we could use to build this network, right? And then we're asked the question, given this subset of edges, basic connections between these nodes, what is the lowest cost network that you could build, assuming that the cost of the network, cost of building the network, is basically the total cost of the edges that are involved in the network. So each edge that we're given as a potential link in the network has a cost associated with it. So this, you can think of this as a weighted graph. It's a weighted, undirected graph, right? So, all right. So we're trying to find the lowest cost network. So there's a question: is Bellman-Ford algorithm is a good idea in relation to this problem? No, that's the Bellman-Ford algorithm we're going to visit later on, and that's also a shortest path algorithm. But this is a different algorithm. We're basically going to look at a way to come up with the lowest cost network that connects all these nodes together. Okay. All right. So let's say that I analyze this problem and I come up with these let's say connections, right? And I claim that this is the lowest cost network that you could put on top of these points. Could this claim be correct? That this network that I'm showing in red, could this be the lowest cost network, considering that all the edges have a positive non-zero cost? It's not possible. Why? Because there's a cycle. That's right. So if you remove, there's a cycle right here, and you're still going to have a connected network if you remove any of these edges in the cycle. So if you remove this edge, and you reduce the cost of this network, you're still going to have a connected network, right? So a network with a cycle can never be the lowest cost network. So what are we looking for in terms of the shape of this network? What are we looking for? We're looking for a tree. That's right. Which basically, by definition, a tree is a connected graph that has no cycles, right? So that's basically the definition of what a tree is. Okay, so this is basically what we're looking for. And so we're looking for a spanning tree, right? And any tree that covers all the nodes of the graph is called a spanning tree. But we're not looking for any spanning tree. We're looking for the spanning tree that has the minimum cost of all the spanning trees. So we're looking for a minimum spanning tree, or what we call an MST for short. Okay. So I don't want to get into the actual solution here because we don't have any time, but this is going to be still under the umbrella of greedy algorithm. So you could imagine that we'll have some greedy solutions for it. Already I see some suggestions on how to solve this problem using a greedy approach. So yes, so we're gonna continue this next time, tomorrow. All right, guys. I will see you soon.